Imagine standing just a few kilometers away from one of the most powerful rockets ever built. The engines are ready. The countdown clock is ticking. Billions of dollars, decades of research, and the dreams of humanity are sitting on that launch pad. And then a tiny leak, not an explosion, not a massive failure, just a microscopic escape of hydrogen, the smallest element in the universe, powerful enough to stop a giant rocket in its tracks. How can something so small challenge something so massive? Today, we're diving deep into one of the most fascinating engineering battles of our time. Why did one of the most advanced rockets on Earth struggle with fuel leaks? What makes liquid hydrogen so brutally difficult to control? And how is a completely different engineering philosophy offering a bold new way to solve these challenges? This is not just about one rocket. This is not just about one company. This is about physics versus ambition, tradition versus rapid innovation, caution versus calculated risk. It's about what happens when human intelligence meets the unforgiving laws of nature. By the end of this video, you will understand why fuel leaks are not simple mistakes, why they reveal deeper truths about engineering, and how the future of space travel may depend on how we choose to solve these problems. Liquid hydrogen is one of the most powerful rocket fuels ever used, but it is also one of the most difficult substances to control. The core problem begins at the molecular level. Hydrogen is the smallest and lightest element in the universe. Its molecules are so tiny that they can slip through microscopic gaps that would easily contain other fuels like kerosene or methane. Even the smallest imperfection in a seal, valve, or joint can become a pathway for leakage. What looks perfectly sealed under normal conditions may fail when hydrogen is involved. The challenge becomes even more intense because liquid hydrogen must be stored at extremely low temperatures, around minus 253 degrees Celsius. At these cryogenic temperatures, metal components shrink. When fueling begins, temperature differences between the supercold fuel and warmer hardware create rapid contraction and expansion. This constant thermal stress can slightly distort seals and fittings, creating microscopic openings. Under high pressure, hydrogen eagerly escapes through these tiny paths. Another issue is hydrogen's low density. To generate enough thrust, rockets must move enormous volumes of it. That means large tanks, complex plumbing, and powerful pumps operating at high flow rates. The higher the pressure and flow, the greater the stress on the system. Even a minor weakness can turn into a detectable leak during fueling operations. Hydrogen is also highly flammable, so even small leaks become serious safety concerns. Sensors must detect tiny concentrations in the air, and launches are delayed at the slightest sign of escape. Containing liquid hydrogen is not just an engineering task, it is a constant battle against physics itself. Liquid hydrogen must be stored at cryogenic temperatures close to minus 253 degrees Celsius, and this extreme cold introduces a completely different layer of engineering difficulty. At such temperatures, materials do not behave the way they do under normal conditions. Metals contract when cooled, and different materials contract at different rates. When a rocket is fueled, the sudden exposure to ultra-cold propellant causes pipes, valves, seals, and tank walls to shrink rapidly. If two connected components contract unevenly, tiny gaps can form at their interfaces, creating opportunities for leaks. The problem intensifies during the fueling sequence. Hardware sitting at ambient temperature is suddenly exposed to cryogenic fuel, producing sharp thermal gradients. These gradients generate stress within the metal structures. Repeated cycles of warming and cooling during tests and launch attempts can fatigue materials over time. Seals made from specialized polymers must remain flexible at extremely low temperatures. Yet even advanced sealing materials can become brittle or lose elasticity when exposed to prolonged cryogenic conditions. Pressure adds another layer of complexity. As the fuel flows, it creates dynamic forces inside the plumbing system. Combined with thermal contraction, these forces can slightly shift fittings or joints that appeared perfectly aligned at room temperature. Even microscopic misalignments can compromise sealing surfaces. Additionally, frost and ice can form on external components due to the extreme cold, potentially interfering with sensors or mechanical interfaces. Engineers must carefully manage temperature conditioning procedures, slowly chilling down systems to reduce shock, yet even controlled processes cannot eliminate all risks. Working with cryogenic hydrogen means constantly balancing temperature, pressure, and material behavior in an environment where physics leaves almost no margin for error. The Space Launch System is built upon heritage technology derived from the Space Shuttle era. And while that legacy brings proven performance, it also carries structural and architectural constraints shaped decades ago. The core stage engines are evolved versions of the RS-25 engines that powered the shuttle, and many design philosophies reflect priorities from a different time in aerospace engineering. These systems were originally created for reusability under shuttle mission profiles, not for a modern, heavy-lift rocket assembled through contemporary manufacturing techniques and rapid development cycles. Using legacy-based components means working within established geometries, materials, and integration methods. Engineers must adapt older engine designs to new tanks, updated avionics, and different structural loads. Even small changes require extensive validation because the original systems were not built with today's modular flexibility in mind. As a result, integrating heritage hardware into a new launch vehicle introduces complex interfaces where tolerances must be re-evaluated and certified under modern safety standards. Another challenge comes from manufacturing approaches. Shuttle-era systems relied heavily on traditional aerospace supply chains, precision machining, and long qualification timelines. Modern competitors often leverage additive manufacturing, digital simulations, and rapid prototyping to iterate faster. When legacy hardware is incorporated, redesigning or simplifying components becomes more difficult because altering one element can ripple through an entire certified system. The regulatory and documentation requirements surrounding heritage systems are also extensive. Decades of accumulated procedures demand rigorous verification for even minor modifications. While this ensures reliability and safety, it can slow troubleshooting and limit flexibility when unexpected issues such as fuel leaks arise. The strength of legacy engineering is its proven capability, but adapting it to new missions demands extraordinary coordination and precision. Before a rocket ever leaves the ground, it must go through a full fueling rehearsal known as a wet dress rehearsal, where the vehicle is loaded with cryogenic propellants under real launch conditions without actually igniting the engines. This process is designed to simulate countdown operations, test communication between systems, and verify that fuel loading procedures work flawlessly. For a vehicle like SLS, the complexity of this operation is immense because it involves transferring hundreds of thousands of gallons of supercold liquid hydrogen and liquid oxygen through an intricate network of pipes, valves, and umbilical connections. During fueling, propellants move from ground storage tanks through long transfer lines into the rocket's core stage. Each connection point between ground equipment and the rocket becomes a critical interface. These umbilicals must remain sealed while handling extreme temperature differences and high flow rates. If even a small seal experiences thermal stress or misalignment, hydrogen can escape. Sensors are placed throughout the system to detect minute traces of leaking gas, and operations are automatically paused if readings exceed strict safety limits. Pressure control adds another layer of difficulty. As tanks fill, internal pressure must be carefully balanced to prevent structural strain. Venting systems release excess gas to maintain stability, but coordinating these processes requires precise timing and automated control. Any anomaly in temperature, pressure, or flow rate can trigger a hold. Because hydrogen is highly flammable, safety margins are extremely tight. Launch teams must constantly monitor environmental conditions such as wind direction and gas dispersion. A fueling rehearsal is not just a test of the rocket, but of the entire ground infrastructure, where the smallest irregularity can halt the countdown and reveal vulnerabilities in an otherwise powerful system. SpaceX approaches rocket engineering with a philosophy built around rapid iteration, simplified architecture, and learning through continuous testing. Instead of spending many years perfecting a design before full-scale trials, the company builds prototypes quickly, tests them aggressively, analyzes failures in real time, and implements improvements in the next version. This method reduces the time between identifying a flaw and deploying a solution. In the context of fuel systems, such an approach allows engineers to detect sealing weaknesses, material stress points, or plumbing inefficiencies early and refine them through repeated cycles. Material selection also reflects this mindset. For example, the use of stainless steel in large cryogenic structures offers strength at low temperatures, while remaining relatively cost-effective and easier to manufacture at scale. Rather than relying exclusively on highly specialized legacy components, the design prioritizes manufacturability and structural resilience under extreme thermal conditions. This helps maintain integrity when handling cryogenic fuels, which place enormous stress on tanks and joints. Another defining element is vertical integration. By manufacturing many components in-house, SpaceX reduces dependency on complex external supply chains. Engineers can modify parts rapidly without waiting for lengthy contractor coordination. Digital modeling, real-time telemetry, and high-speed data analysis support this process, enabling teams to observe exactly how systems behave during fueling and testing. The company also simplifies plumbing and structural layouts whenever possible. Fewer joints, fewer interfaces, and more streamlined pathways reduce potential leak points. This combination of iterative testing, material strategy, integrated production, and design simplification creates an environment where technical challenges are confronted dynamically, rather than being locked into long development cycles. Innovation in aerospace can follow two very different paths, one driven by strict tradition and institutional caution, and the other driven by rapid experimentation and calculated risk. Large government programs often operate within highly regulated frameworks designed to minimize uncertainty. Every component must pass layers of certification, documentation, and review before implementation. This approach prioritizes reliability and long-term mission assurance, especially when human lives and national objectives are involved. However, the same caution can slow the process of diagnosing and correcting recurring technical problems, because even small design adjustments may require extensive analysis and approval cycles. In contrast, a risk-tolerant innovation model accepts that controlled failures are part of progress. Instead of preventing every possible malfunction before testing begins, this philosophy allows real-world trials to expose weaknesses directly. When a flaw appears, engineers respond quickly, redesign the affected system, and test again. The learning cycle becomes faster, because experience is gained through action, rather than prolonged theoretical preparation. Over time, repeated testing builds confidence through accumulated data rather than through extended paperwork and simulations alone. Both strategies aim for safety and performance, but they manage uncertainty differently. A traditional system reduces risk up front through exhaustive validation, while a rapid iteration system manages risk dynamically through frequent testing and incremental improvements. In complex challenges like handling cryogenic fuels, the difference becomes visible in how quickly teams can adapt to unexpected leaks, redesign interfaces, or modify procedures. The balance between caution and bold experimentation ultimately shapes how efficiently technological obstacles are overcome. As we have seen, the story of fuel leaks is not a story of failure. It is a story of physics, engineering limits, and two very different paths to innovation. Liquid hydrogen challenges even the most advanced technology because it pushes materials, seals, and systems to their absolute extremes. Cryogenic temperatures test the strength of metal. Legacy designs test the flexibility of modern integration. Complex ground systems test precision under pressure. Every delay, every leak, and every hold in the countdown is not weakness. It is a reminder that space exploration operates at the edge of what is physically possible. At the same time, we see how a new generation of engineering philosophy focuses on speed, iteration, simplification, and bold testing. One approach builds confidence through decades of procedure and validation. The other builds confidence through rapid experimentation and continuous improvement. Both are driven by the same ultimate goal: to push humanity beyond Earth. This is what makes space exploration so powerful. It is not just about rockets, it is about problem-solving at the highest level. It is about refusing to surrender when physics fights back. Every leak fixed, every system improved, every lesson learned brings us one step closer to deeper space, to the Moon, to Mars, and beyond. To everyone watching, keep questioning, keep learning, and keep aiming higher than the sky. The future belongs to those who dare to understand it.